Hello everyone, this is Kerchen, your TA on CSE 251A. Today's discussion session will be mainly focused on the vector calculus and the gradient descent methods. So let's catch up some basic manipulations of the vector calculus just as a warm-up. Suppose that we have two column vectors, A and B, and we have three metrics, A, B, and C, capital one. So the basic kind of things we need to mention is about the multiplication. So suppose that two metrics, A and B, times together to become the metric C. So what will C be like? That's the question. So suppose A is an n-row m-column matrix, and B is an m-row k-column matrix. The C will be an n-row k-columns matrix. One restriction here is that the columns of the A, the number of the columns of A, m, should be equals to the number of the rows of the B. This should be maintained. Then we got the C metric as the multiplication, where each entry value of C is equals to the sum of a group pairs of the A entries in A and B. So this is a little bit abstract here, complex here. So how to visualize it? So suppose that we have a metric A and we have metric B. So usually there's a way to visualize is that C will be settled here. So how to get C? Suppose that we want to get the entry of the C11 here. It will be obtained by A11 times B11 plus A12 times B21 plus A13 times B31 and so on. Then we got this kind of number and sum them together, which means that each entry value of C will be the summarization of the element-wise multiplication of each column, each row of A, and each columns of B. Suppose that we have this entry value here. This will be obtained by this row and this row, and doing the element-wise multiplication and sum them together. This will be a demonstration of how we can visualize the multiplication process of A and B. And this will be very useful because when we try to use different rules in the vector calculus or metric calculus, it will be very helpful to make you understand how it's going there. And second thing we need to mention about is the distributive feature, which means that when we have three metrics, A plus B times C, it will be equals to A times C plus B times C. This means that multiplication of the matrix is distributed. And we can extend this kind of things into the vector, which means that if we use two vectors, A taking the transportation and times C, it will be A taking the transportation times C plus B transportation times C. So the reason we use the transpose here is that previously, like in that definition, we usually define A and B, the vector A and B, as the column vector, which is look like this one. So you need to take the transportation become like a row vector and times the matrix. Then it becomes something you like have here. And one thing important here is that the multiplication of the matrix is not commutative, which means A times B is not equals to B times A. And it can be easily visualized by this way. So you can see here we have A, and here we have B. So A times C will be this one. But if we use B times A, we got another matrix. So this matrix is not equals to this matrix because you can see this value will be the row of A and the column of B and taking the element-wise multiplication. But this value will be the row of B and the columns of A in the first entry. So that will be not equal. So that's not supposed to be like a communicative feature. And we have the transpose. Usually, if we want to take the transpose of the multiplication of the matrix, it will be something like we take the order, reverse the order, and take the transportation of each of them. This means that if we have originally, A and B as the matrix, and we take the transportation of them, which means it's equals to, we reverse the order, B from AB to BA, and take the transpose to each of them. And the reason here is, again, visualization. We have A and B becomes A times B. You take the transportation of the result, which means that you flip this kind of like column, switch the axis. This was also means to switch all the axes from A and B, which means that reverse each of the axes independently, which is becomes BT and AT times scalar. So that would be a very good demonstration. And also, we can have different extension, which means that if we extend this to be like the vector, the two vectors, the row vectors times the column vectors will become the scalar. And we take the transportation of the scalar, that will not be changed, right? The transportation of the scalar is still being a scalar, which means A transportation B will be B transportation A. This is the capital T here, sorry. So which means that ATB is equals to, original, the transportation of it. So this will be like another kind of extension. And also, we can also have, a more kind of like the extension. You can have 3 variables and you take each of them and take a reverse. Reverse the order and then take the transpose of each of them. And that's the basic multiplication. If we want to take the derivatives of the vector, how to calculate that? Before we go into the derivative mentions of the vector, we can just recap some derivative methods of the scalar, which means that suppose that we have a constant scalar b, suppose that we have a variable scalar x, and then we have the scalar derivative like this way, like f(x), and we take the derivative of it will be df divided by dx, right? And this will be extended to different kind of rows, so we have different examples. When we have a function as the bx, its derivative will be b, only taking the constant out. If we have x squared, according to the rules, we can have 2x as the result, as the derivative. And if we have like bx squared, which means that we first take the 2x out and then we take b out, we have 2bx. And now we take an analogy. So only thing you want to memorize here. Suppose that we have a constant column vector b, both b. That we also have maybe constant matrix b, capital B. And we have variable, column vector x. So when we take the derivative of the variable x based on different functions, we actually have the same way, like fx is equals to df by dx. So taking an analogy, all you need to memorize is if we have the bx analogy into the vector calculation, x transpose b or x transpose b vector, the derivative of it will become only the matrix b or the column vector, the constant column vector b. If we have x squared in the vector, which is x transpose times x, the derivative of it will be 2x. And again, if we have the analogy of the bx squared in the vector calculation, which is x transportation times b times x, it will become b plus b transportation times x. This will become a cheat sheet of how you calculate the derivative of the vector calculus. And in the next page, we'll try to go over the details of it for why it will become this kind of things, how to calculate the derivative of the vectors. So again, we go into some detail of it. So we have the constant column vector b, constant matrix b, variable column vector x, and the derivative df dx is equals to what? Here, we want to change f to y. The y will become something of the function of x. So suppose that y is the scalar. So sometimes that the function of the vector will become like the scalar, which means that if y is the scalar, the derivative of x, dy divided by dx, here y is a scalar, x is the vector. This will become taking the derivative of each entry of the x according to this kind of y, which means it's dy by dx1 in the first entry, dy by dx2 in the second entry, and again, and dy by dxn in the n entry. And this is the row vector. So we take the transpose to become like the column vector. And this will be the derivative of x when y is the scalar result. So that's why we have some explanations for the x transpose times b, the derivative of it will become the b, right? Because if we take x transpose b, it will become the x transpose and b like here. So the result will be equals to x1 b1 plus x2 b2 and plus xn bn, right? And you take the derivative of this y, it will become in the first entry, you take the y, dy by dx1, it becomes b1. And in the first second entry, take the derivative of x2, becomes b2, b3, and and become bn. And you take the transpose of it, which is b here. And we can also explain why xt times x and the derivative of the xt and x is 2x, because this will become the summarization of x1 squared times x2 squared times x3 squared times xn squared. This is the result. It's the scalar. And you take the derivative of this y, right? And it will become what? 2x1, 2x2, 2x3, and 2xn. It will explain like why we can get the derivative of this to become this one. And this will be a little bit complex. I'm not gonna go to the much detail of it, but if you yourself like go take the derivative a second way we introduced in above, it will found that the final result will become this one. So all this result, xtb, xtx, xtbx, will become the scalar. When we take the derivative of the vector according to a scalar, it will become like this kind of things. They take like the derivative of each entry of x and then reflect into each entry in the final result as a vector. So if y is not the scalar, the y is a vector, it's the row vector here. Here we want to mention one thing is that we define here is that y is the row vector, but sometimes in some materials we define like directly define yt, which means that suppose that y is the column vector and yt is the row vector. So if y is the row vector and x is a column vector, if you take the derivative of the vector x according to y, you will get the matrix. So how to understand this matrix? The y is the row vector, so they become y1, y2, y3 to yn, right? Suppose that y is the m dimension vector. And then one thing here is that you just treat it like the scalar. Each of it is the scalar result, right? Which means that you take y1 and take the derivative by x, which is become this column. And you take y2, become this column. y3, y4, and then yn become this column. So here, all you need to memorize is that if y is the vector, x is also the vector, the derivative of x according to y, dy by dx, is the matrix where the row is ordered by y index, and the column is ordered by x index, y1 to ym from x1 to xn. This will be the understanding. So let's also explain why we have this result. And let's end up the topic of the vector calculus. So if you have more questions, you can also ask in the Zoom office hours and also in the Piazza. And next, we'll go into another kind of like the topic. It's called gradient descent. So we have some materials and discussion in the lecture for about gradient descent. And then here, we just want to discuss how to understand the pseudocode of the gradient descent. The first general gradient descent is the batch gradient descent we talk about. So the pseudocode will be like this one. First, we pick an initial value of weight. We call like W0. And then we have a learning rate, alpha. So we just constantly like continue a loop until it got convergence. The next stage of the weight will be updated by the current stage of the weight minus alpha learning rate times the gradient of your loss function. And here, this loss is taking the average of all data points you have in the training set. Suppose that you have capital N data in the training set, and you take all data into that, calculating the loss, and taking the average of it and become a gradient, and then you update this kind of value. So suppose that in the beginning, you have the weight here. So this will be the cost. So the optimization problem is that we want to find an optimal W that can minimize the cost, right? So in each time, suppose that you are in this kind of like the weight value. So you take the gradient of it. So why it is minus? So you take the gradient of it, it will become the slope here, right? So the slope here will be smaller than 0 because it's like the negative like pressure weight. So which means that if you minus this number, it will go into that optimal or minimum value a little bit, like from this way to this way. And then you got a new kind of slope here. You minus it, it will become this point. Again, then it will achieve the minimum. So this is like the basic like method or definition of how gradient descent is working and why it's called like descent here. And the basic gradient descent we also called batch gradient descent, which means that the size of your batch is capital N, the total numbers of your training set. The problem is we don't have enough computation cost when the N is very large, because in a very modern training of like the machine learning or deep learning method, usually the data will be very, very large. It can be millions of like data points or even like 100 millions of the data point. So in this kind of things, we cannot calculate N in one batches, which means that it will be very costly. So to replace by this way, we can use the stochastic gradient descent. What that means that all the things will be the same. The only kind of difference will be for the update rules, we did not include all the N data. We only randomly pick one data sample from the data set, and we use this to update the weight. So different from the batch gradient descent or general gradient descent, the batch size here is equals to 1. Each time, we randomly pick the data sample, and then we update this kind of gradient descent. So compared with like batch gradient descent, the stochastic gradient descent, we have like advantage and disadvantage. So the advantage of the stochastic gradient descent is that it will be very efficient, because each time we need to calculate only one batch size like gradients, and then we take the update of the weight. But that also leads to the disadvantage of the update of the stochastic gradient descent will be very unstable and unsafe, because each of time it will only find the local optimization of one data point. But sometimes that this data point may not reflect the whole trend of the update rule, which means that the whole trend of the update path will be like this one, like the batch gradient descent look like. But this stochastic gradient descent will try to approximate this because they just have each data sample to provide the direction, but that direction will not be exactly the same as the whole data tells you. So this will be a little bit unstable. Sometimes that if you use the SGD, you will not try to approximate your final local minima of the weight. So how to make the balance of it? We have a trade-off, right? We trade-off is the mini batch gradient descent, which means that we don't need to pick one value as the batch size, and we don't need to pick all data samples capital N. We pick a small n here, which is more than 1 and smaller than n, capital N. And then we have n data samples, small n data samples, and we update this rule by using the current weight and calculating the loss function of n data samples and take the average of n and then become a gradient, and then we can use this kind of like the rules to update the weight. So compare with the batch gradient descent and stochastic gradient descent, the mini batch gradient descent is more smooth than stochastic gradient descent. They can maintain a very biased like directions of your optimization path, but they can save the computation. And still, if you choose different mini batch, right, sometimes 12, 16, 32, 64, it will have different like the result, because when you calculate this kind of pathway, sometimes it will become like this one, and will become this one, and approximate to true optimization of the batch gradient descent. So there's just like three kind of like difference. Batch gradient descent, batch size is equals to capital N, the whole data number. Stochastic gradient descent, SGD, is equals to 1 with the batch size. And the mini batch is equals to N, where N you can define a number, and basically you will find the practical, parameters when you write the code about it. Sometimes it can be 16, 32, 64, 128, and they can be different number you can choose, depending on your resources and your computation cost. And that's all about like the gradient descent. So please drop in like the Zoom call, and we have the office hour of this discussion on Thursday from 6:10 p.m. to 7 p.m. And the Zoom link is in the Piazza announcement. And welcome there, and you can ask any question, any additional question further about this kind of discussion. And thank you very much.